So thanks for the kind invitation to this wonderful conference. It's great to be back in this fascinating place in Vienna. It's also great to literally see you as a three-dimensional sensation. I've become too much used to the idea that the world was two-dimensional. And also apologies for rushing in today. I had to be in Eisert for the Munich Quantum Valley this week, where also Frank Pollmann is, but it is what it is. So there's good news and bad news coming along with this talk. The good news being that we should be pretty much spot on with our topic when we have a look at ideas on tensor networks to capture entanglement in quantum many-body systems in mathematical structures and novel algorithms. The bad news is just that we have a look at some fun new ideas on tensor networks. So there will be a bit of an overview component when we meander through the theme, like presenting some ideas that we have had in mind in the past year. And I know that overview talks can sometimes be kind of second best, but given the scope of the workshop and that we are close to the wrap up at the end of the week, I thought it would be a good idea to follow this path, showcase that tensor networks are really very much alive and kicking, so that I could kind of say things that are fascinating recently. So good. The reason we are here is that the tensor networks capture common entanglement patterns in quantum many-body systems. That's particularly clear in one spatial dimension where matrix product states, MPS, many paper states, basically capture one-dimensional phases of matter. Surely Hilbert space is huge, but that's kind of missing the point that the states we are interested in sit in a teeny-weeny corner, like the physical corner of Hilbert space. And there's a wealth of mathematical and numerical insights emerging from that. In two spatial dimensions, it's kind of similar, or the kind of mathematical rigor in some ways is kind of slightly less, but here we're in the realm of projected entanglement pair states, perhaps where, again, a wealth of numerical insights follows, and also mathematical ones, and again, which is one of the reasons we are here. So in this talk, I will be trying to throw in two somewhat fresh, unorthodox ideas along this line in three readings. The first being that like randomness can be a very nice tool we put on the mathematical head here, and we see that randomness is an enormously powerful tool to basically prove things that are really hard to come by in other settings, it seems fair to say, invoking some sort of notions of typicality, somewhat inspired by ideas of quantum statistical. In the second, much shorter part, we will have a look at tensor networks to assess properties of real quantum materials, where the fun part mostly comes in because we closely collaborate with Bella Lake, who's really synthesizing quantum materials in the lab, where we do tensor network simulations for her. And then she's great because she can not only do these experiments, but she can also talk theory and talk tensor networks, so that's a nice collaboration to have. And finally, we will see, like that's the most conceptual part, hi Caro, good morning, where we think of how tensor networks can be used in quantum machine learning inspired settings, where we more concretely learn classical and quantum dynamical laws from data using tensor networks. Good, but let's get going on random tensor networks. Now the upshot here is that one uses randomness as a tool and asks how this can be harnessed to explore typical properties of tensor networks in one way or the other. And that comes in many flavors and forms. So random tensor networks are seen as a kind of a proxy for the real thing, but one that captures many things of the real thing, but in a way that's easier to capture in mathematically rigorous terms. For example, random quantum circuits do show features of quantum chaotic dynamics as it's being like witnessed by out-of-time ordered correlation functions, many-body localization, and so on, in the way that some people wouldn't even discriminate between the random quantum circuit and the real thing when they talk about some underlying physics. But again, it's easier to capture in mathematically rigorous terms. Or random tensor networks can be seen as kind of typical or providing typical states of matter in phases of matter. One can think of holographic descriptions in one way or the other, and that's what we have in mind for the first part of this. So, what is a random tensor network? It's a tensor network with random entries. And what could be more natural than thinking about a random many paper state, a random matrix product state, where you have a one-dimensional structure and you pick a certain probability measure, and you draw specimens instead of this probability measure and place these tensors one by one onto the system. Also, David Monik has done very nice work along these lines, and you kind of see what happens. It depends, of course, on the probability measure. And the most natural probability measure of that would be one where you basically see these tensors as isometries, have a dummy index to the top, and then you draw the unitaries according to the Haar measure one by one. That's a very natural measure in many ways. And you can see this family of states that's emerging in this way as being the ground state of a family of disordered Hamiltonians, but think about this as you like. It's a meaningful measure of random tensor. And for this, one can actually show many things, and things that are really difficult to come by otherwise, and that's kind of the claim that I'm making. Let me focus on one example mainly, which is in the context of quantum statistical mechanics, basically in the context of the question how properties of quantum statistical mechanics on the one hand with maximum entropy state and equilibrium on the one hand would be in contact with out of equilibrium dynamics generated by many-bodied local Hamiltonians on the other. You have a question?
Yeah, so is the reason that you take unitaries because then you know that all these states are normalized, all these random states?
Not really, but that's a nice feature to have. Indeed, we are.
Or it's an infinite system, so you know they're all normalized. Or...
That's right. That's a nice feature to have. Yes, I mean that's one of the reasons. But the other reasons will come clear in a second. And the context we're in is like kind of trying to bring together statistical mechanics properties with non-equilibrium properties. Of course, that's not a new question. Even this gentleman here in the 1930s was kind of looking at that with a famous paper, seeing that if you think of many-body dynamics, you should not expect this ever to equilibrate, truly. But what's good enough to make the contact of statistical mechanics is that if you make measurements, that most of the time the expectation value will be very, very, very close to the average, so the infinite time average, to kind of resolve this seemingly clash between stat-mech and out of equilibrium dynamics. So a bit in more concrete terms, you would take measurements in the lab. Never let the theorists into the lab, but you take measurements, and if the measurements are close to the time average with teeny-weeny fluctuations around that, then you would say the system would fluctuate. And there's a long tradition about this, and lots of papers, and it's conceptually quite clear. However, it's very difficult to say anything in rigorous terms about that proves that this is actually what is happening in an actual system. And with tensor networks, one can make quite some progress on actually proving that this is happening and that the fluctuations become small. The system would nicely equilibrate. In fact, not only that, it equilibrates well. If you start from a random matrix product state and evolve this under generic Hamiltonian in time, but not only that, it would equilibrate exponentially well, meaning that the in a sense of a large deviation bound, the probability of deviating a little bit from the average, from the infinite time average, would be exponentially suppressed with a factor that only depends on the physical dimension and the bond dimension of the matrix products. So that may not be surprising. Surely many-body systems tend to equilibrate, but it's one of the few settings, generalizing beautiful work also by Eric Mario and so on, that shows that this is actually happening in a rigorous fashion in a specific many-body system. So, yeah.
Do you have to assume anything about the Hamiltonian to?
Only that it's kind of generic in the sense that that there's not too many degeneracies in the gaps and so the difference between the spectral values of the Hamiltonian. That's the only assumption that you make. Otherwise, it's completely generic. But that's the single.
Like locality or so?
No. But of course, the times there's a lot to say about this. But the theorem doesn't assume anything except the gaps are not degenerate or not too degenerate. Okay, so time is short. I will not go too much into detail of the proof, but on the highest level. So starting point is the so-called effective dimension that basically is a polynomial of fourth order that captures, say, how many terms. It's really an effective dimension in the sense that it captures the number of terms that would contribute if you expanded the initial state into many-body eigenstates of this unknown many-body Hamiltonian, as U2 nicely points out. And this is the hard work comes in when you want to compute moment operators. So they can be written in terms of Weingarten calculus, and the hard work, the inside, builds on nice work by Nick Hunter-Jones, who is able to formulate these moment operators in terms of partition functions of classical statistical mechanics models, where we uplift this to the tensorial setting, where we have the tensor network setting in one dimension and the order of the polynomial in the other, and then using tensorial calculus, one can indeed formulate this large deviation bound as a rigorous bound that depends only on the physical and the bound. This is nice. This shows that indeed one has exponential equilibration in the model, even though this is not too surprising, but it's a setting where this can be very nicely proved. There's other things like explains entropies. One can get insights into phases of matter and so on, but I will not go into detail here. I'd rather ask another question that's related, namely, say, how does the complexity grow for random quantum circuits? And that's a question that rose to quite some prominence for reasons I will say in a second. So the circuit complexity comes in many forms and flavors. The most simple one, and that was also the historical first one, asks for a given unitary, how many unitaries from a given gate set you need to exactly represent the unitary. That's of course a nasty quantity. I mean, it makes a lot of sense mathematically, but it's very hard to compute. It's actually computationally hard to compute because there's could be like funny, you make entanglement, you undo this, there's funny cancellations, it's not easy to compute. It's related to the T count question that asks how to cut a unitary into Cliffords and T gates, which is something that the Microsoft group in Washington does full-time. And this is not in NP, but there's no polynomial time algorithm known for the T count game. So this is hard to compute, impossible to numerically assess, but it makes perfect sense. It's related to the computational complexity of a unitary. Given a unitary, how many gates do you need to write it out in terms of unitaries? Now, the point why this question of the complexity of random circuits rose to prominence is actually due to these gentlemen here, Brown and Susskind, in particular Susskind, one of the founders of string theory, a very flamboyant person who gives wonderful and inspiring talks, where he was like wondering in the context of the ADS-CFT correspondence, that's a kind of dictionary between Einstein gravity in some dimension and a conformal field theory in one dimension or less. And he was like looking at the eternal black holes and was wondering what in what way the volume growth of wormholes on the ADS side would correspond to what on the quantum side. One knows that the volume of the black hole of the wormhole would grow linearly in time until exponentially long times. But what is it on the quantum side that would grow linearly in time until long times? Yeah, and I mean, entanglement it can't be because that would saturate quickly. So they thought it could be complexity that grows for a long time and that would eventually saturate. That came to prominence as the Brown-Susskind conjecture, but it's like extremely difficult to prove. Here's the upshot. They said one would expect the random circuit to have a linearly growing complexity. And this makes sense. Of course, every circuit is its own description. Yeah? But the question is how much you can compress. But, I mean, Hilbert space is a big place. So how unlucky can you be with a random circuit to go too much back so you would explore new territory over and over again until you're at a point where you're basically sampling out Hilbert space and then it would eventually saturate. And that's what the Brown-Susskind conjecture was. The random quantum circuits have a linearly growing complexity, which makes a lot of sense, but it seems impossible to prove. It's also numerically, I mean, we tried this for 3 qubits, even that doesn't work. And it seemed like impossible to prove because it's a hard problem, so how would you even come about it? But interestingly, it does grow. The linear growth conjecture is true. It's proven true until exponentially long time. So a random quantum circuit would have a linearly growing complexity and would then eventually saturate. Okay, so how's this proven? I give a kind of maybe a high-level upshot, but I'm happy to say more about this. It's kind of a insight. Like Jonas, the fourth student of Christoph, played in the role. So the complexity is a beast. So we looked at a slightly less beastie property or object, the so-called accessible dimension. And here's the point. You have a unitary gate set and you place this on the circuit, say a bricklayer circuit, and if you the accessible region within the unitaries, if you turn the knobs of the unitaries, give rise to some set. It's not a manifold, it's a nasty fingery set, but well, it's a reachable set, and it's a so-called quasi-algebraic set, meaning in one way or the other, it's defined by a number of inequalities and equalities. Say quasi-algebraic sets, think say of a unit disk in 2D, and this accessible dimension is the dimension of the largest manifold that is in the foliation of this set. Say, think of 2D, the unit circle, then the unit disk, the unit circle is a one-dimensional manifold, the open disk is a two-dimensional manifold that would have accessible dimension 2. Okay, so much of the heavy lifting is done by the so-called Tarski-Seidenberg principle that says if you take a quasi-algebraic set and map it to a new set under a polynomial map, this will be another quasi-algebraic set. And using this, one finds that, in fact, almost all circuits would happen to have the maximum accessible dimension in the way I've just explained. But this is a big step, because now you don't optimize over all possible gate decompositions, which is impossible to do, but you just say almost all circuits have the maximum accessible dimension anyway, which bounds the complexity, and you just have to find one generic enough example of a random circuit that has that property. And what could that be instead of, if not random Clifford gates, where that's actually much of the hard work. You take Pauli's and then you conjugate them to the Clifford circuit and ask how many independent directions you have to bound the accessible dimension. But that is generic, and then you see, indeed, the complexity grows linearly in time until exponentially long times, proving the Brown-Susskind conjecture. And again, that's something that's really hard to come by otherwise, like with Hamiltonian dynamics, but here it's a proven instance of a complexity statement that the Brown-Susskind conjecture is actually a proven true statement. So that's something that Caro has mentioned in her talk earlier this week, that tensor networks or random tensor networks also provide a nice playground when thinking of toy models for the ADS-C2 correspondence, where one, for example, can think of tidings of the negatively curved plane and place like match gate tensors there that are basically free Fermi tensors, and where we can go a long way of actually spelling out an ADS-CFT correspondence in terms of tensor networks. You start in the middle and you go layer by layer. You can formulate inflation rules, and using that, one can actually get even a formula for the entanglement entropy on the boundary of subregions in perfectly analytical and rigorous terms, which is nice because usually it's very difficult to combine analytical terms. So what Kara's talked about, if I'm right, was a nice way of going to the continuum and thinking of random match gates, where one can go as far as actually having closed form analytical expressions for the continuum critical quantum field on the boundary in terms of random tensor networks. Is that right? That's what you were talking about earlier this week, which is nice, again, because it seems not easy to formulate critical tensor network models in the continuum that has been around. So to wrap up this first part, So the lesson is that random tensor networks are nice. They're a fun playground for rigorous studies. And the point I was trying to make, it's a setting where one can prove things that seem out of reach otherwise. And it's a proxy for the real thing often. It's not the real thing, but once one is willing to go to the realm of random tensor networks, you can show things, do things that seem out of reach. Otherwise, it seems fair to say. Which brings me to the second and short part, because I want to leave time for questions at the end. I'll overrun on tensor networks for quantum materials, where we set out to, but we change gears. We go away from the rigorous mathematical perspective and think of numerical implementations, where we think of using tensor networks to explore experimental quantum materials. Again, where we join forces with Bella Lake, an experimentalist at the Helmholtz Center in Berlin, who's actually synthesizing interesting quantum materials like a double-layer Kagome spin liquid with funny ferromagnetic and antiferromagnetic couplings. She talks about these materials like other people talk about their dog. It's kind of cute to see that she's really familiar with these things, but she also speaks theory and can interface with theoretical studies, and we made it a mission to help her understanding these quantum materials by tailoring tensor network methods to the systems she has at hand. And we started out from looking like a PES algorithm that was like using certain triangles, that was looking at magnetization as a dependence on the applied magnetic field in this kind of funnily frustrated double layer spin liquid. So that's nice, and the cute thing is that one can really kind of tailor the tensor network method to the experimental prescription they have at hand. And that's nice because often we talk about models and abstract models, which is great, but it's also good to see that these ideas work for actual quantum materials that actual researchers have in actual labs, and see how that corresponds. It was a nice first baby step, but people said, yeah, right, that's great, but the temperature is low. I mean, they have dilution fridges, that's very low, but it's not zero, so that has an impact. So we were looking at, say, finer temperature simulations with PEPOs. This will come out anytime or next week or so, where we checked how one can describe, say, magnetization curves for quantum materials at finer temperatures, and relating that to measured curves in the experiment with a nice agreement, which is again nice because, once again, we're not talking about abstract models, but actual experiments that you. Or we've been dreaming about how one can think of many-body localization in actual materials that have been synthesized, with the doping giving rise to the disorder mechanism. And of course, the make or break issue is whether phonons and heating will kind of kill the many-body localization in a way. But there's some evidence that if properly done, and if the phonons are suitably localizing, then one might have localizing properties even in a quantum material in the lab, and that's just being synthesized in this very moment. Yes, thank you.
So are these all Mott insulators, or are there also itinerant fermions? Are these all Mott insulators, or do you also have itinerant fermions?
So they're not. Some of them are critical models, so they're not Mott insulators.
Sorry, they're what not?
They're not. They're critical. So they're not Mott insulators. Okay. There's a wealth of.
So this is then all fermionic tensor networks that you use to study these.
No, this is not fermionic actually. This is a spin model.
Okay.
Yeah. We have I come to that in the next setting. We have also code that's versatile enough to have fermions and spin, but that's actually it's a 2-layer spin model. So that's what I was mentioning. We are setting up a kind of toolbox and a library that we are planning to make public, or as a library of corner transfer matrix renormalization group methods based on automatic differentiation. That's pretty flexible. It's good enough for different unit cells and so on. That can be put in as an input to the problem, where the CT-MAG tensors can be computed in an appropriate fashion, where again automated differentiation is coming in to compute the environments. This should be online anytime, and this is meant to be as a service to the community, as a toolbox to do PEPS construction using automatic differentiation that's open to use for everyone. So, lesson. It's fun to see ideas on tensor networks related to features of quantum materials. Here again, the nice thing is, and fermions come in as well, maybe to come back to this. fermions can be constructed with the same efficiency as spin models. A bit of a debate some years ago, but indeed one doesn't need overheads, but one has to bookkeep appropriately the parity information in the tensor network, but that's basically the same as a spin tensor network. Let's ready to proper features of quantum materials. There's some hope that many-body localization can be done in quantum materials. That's nice because, again, that's being done in highly synthetic lab thingies, like Emmanuel Bloch does that in quantum atomic settings. It's far from clear whether this can be done in a quantum material, and this is some contribution towards the quest whether this can be done. Let's see. I'm quite excited. Well, it's hard to assess, but we made our contribution. 25 minutes into the talk, which brings me to the end. I leave some time for questions. This is the third part, which thinks of tensor networks in somewhat machine learning inspired tasks, although there's more to say about the machine learning side. I will cut that out, but rather focus on one reading of the question that I find cute and interesting. And that's the question, how one can scalably learn dynamical laws from data. And that's not a new question. I mean, if you look at these, when Kepler was looking at these funny points moving around on the sky, it took the genius of Newton to find out what the dynamical laws are underlying these funny points moving around. But, well, with the genius of Newton, you could do that, but if you have a many-body problem that has many degrees of freedom coming into play, it's not so obvious what the underlying, say, right-hand sides of differential equations would be given an observation of a many-body system. Far from obvious how to see what the underlying law is if you observe a problem. Or what's the Hamiltonian in the first place? Now this is a question that's of course much seen in the context of quantum technologies where people do like analog quantum simulation and they say they have a Hamiltonian in the lab and they can probe nice properties of this in the lab, but then they say, great, but is the Hamiltonian that you have really what you think you have in the lab? So how can you learn a Hamiltonian from data? But that's even conceptually interesting. Like I've literally never given a single course on analytical mechanics or quantum mechanics, say presenting the Schrödinger equation, where not some smart student would have said, yeah, great, that's Schrödinger equation, but what is the Hamiltonian? And I say, it's given, it specifies the system. And then a student would say, yeah, great, but how do we know? I mean, if you go to the lab, there's no voice speaking to us that gives us the Hamiltonian. Well, maybe there is, but then we have another issue. So it's kind of formulated the wrong way around, if you want, right? It's how the history of physics developed, but oftentimes you really have data, that's all we have ultimately, data from experiments. How are we going to learn Hamiltonians from data? And that's a very interesting question. Good, so in the classical realm, you have to have, you say you go into some lab, not me again, yeah, I'm staying away, but somebody else goes into somebody else's lab and takes the data and assesses like right-hand sides from differential quotients and then asks, can we identify the governing law from observations of snapshots in time? How would you do that? Well, you would need a right-hand side of a differential equation. For that you need functions, and for functions you need dictionaries of functions. So you would pick a dictionary of basis functions, like polynomials, Chebyshev polynomials, your favorite, and then you would try to construct a transformed data matrix and determine the coefficient matrix that best fits, say, in the common sense, the observations that you've made. So, a least square fit. If you want to be fanciful, you would regularize that with a lasso, as people say, like with a one norm that basically finds the sparsest explanation, the Occam's razor, simplest explanation given the data type. It's like super simple, pick a dictionary, make a best fit, but this has a name, it's called SINDI, like sparse identification of dynamical data. It's hugely used and cited. That does that, and that really works well for small systems. You pick your dictionary and you have your, your chaotic circuit and you observe it, and then you see that you can really recover the dynamical law based on observations of that setting. And that's really used in mathematical biology in lots of fields in a nice way. And of course, it makes sense. Data is all we have. You want to have a tool to learn dynamical laws from data. It works really well for small systems, but for large systems, there's an obvious curse of dimensionality coming in, as we expect. It's an exponentially large set. So we need a hypothesis in the first place to even know where to start. Now, this being a tensor network meeting, what else could this be than a tensor network? That makes a lot of sense, getting intuition from the ideas of locality and so on that we have from the quantum realm, but now applied not to the quantum realm, but to the classical realm, where you think of a tensor network and the dictionary functions coming from a tensor network, but where the physical legs are not complex valued legs from a quantum degree of freedom, but legs that label elements of a function dictionary. And then you uplift this to the many-body context of a many-body function dictionary by means of a tensor network. These are the basis functions. There's a lot also coming in for the coefficient tensor. There's several ways you can incorporate this. There's different matrix product ansatz that we've explored over the time. I'm happy to say more about this. The ranks of the tensor networks come in a very delicate fashion because the data tensor is huge. There is some fun things to say. But again, you're basically using a quantum-inspired tensor network, but not for quantum systems, but for systems where the legs are elements of function dictionaries. This gives rise to example. Now, again, the ranks come into play, and they are very important and tricky. So we've made the best experiences with stabilized alternating least squares settings, which are like state-of-the-art methods to look at NPS and NPO manipulation in cases of very strongly non-uniform ranks, and looked at this. For example, in the many-body setting, where you pick Chebyshev polynomials and you really get a good recovery of a system. You observe things, and then you see what happens, and then you say for a model of beds and springs that are coupled by nonlinear oscillators, you would see them, you would model them, you take data, and then you take a many-body function dictionary that would take, for example, the 4 Legendre polynomials per site, and then you uplift this to a many-body function dictionary, and say, can you learn the dynamical law, this nonlinear law from data? And you can really nicely recover this and do this, but now in a scalable fashion, because I made my point. The tensor networks are being used to have meaningful hypothesis classes for function dictionaries. And this works very well, and there's a lot to say about it. But yeah, I mean, this is we've done some work on this, so using tensor networks, but can learn classical dynamical laws. Again, that's not quantum mechanics, it's quantum inspired if you want, but again, the legs are labeling the function dictionaries. But there's also interesting questions coming in from the mathematical side. You can ask for questions about expressivity or entanglement in function space. We know these beautiful, and everybody in the room knows these results, that if you have any entropies with a parameter smaller than 1, scaling like an area law, we know that there is an MPS that approximates the state up to a constant error in the trace norm, and so on. These cute results, they carry over to function spaces, and that's an interesting setting of thinking of locality and entanglement, but in function spaces. I find that quite interesting, and there's a lot that carries over from the Now, last point, how can quantum Hamiltonians be recovered? That's what I said. Again, the quantum technology people want to know this. They have labs, they have data, and say, what is the Hamiltonian? Now, oftentimes you really know quite well what you have. Of course, there's physics. I mean, don't mess with experimentalists. They know what they're doing. I'm being recorded, so no stupid jokes, but of course they know what they're doing. Yeah, but the question is, do they really know what they're doing? Meaning, can you really, if you want to uplift this to the quantum technologies and want to have predictive power in your quantum simulator, you better know exactly what the Hamiltonian is doing, what the Hamiltonian is to very strong accuracy. And again, how can you learn this from data? Now we have 2 readings of this. and they both evolve or circle around taking snapshots of data in time. You go to the lab, you take snapshots in time of meaningful observers, and then you try to, up to some tolerance, you try to recover the Hamiltonian from a meaningful set of Hamiltonians called concept class. In that context, you want to recover the family of Hamiltonians. So there's a lot to say about this, and we have a paper out that came out last week. It has nice theorems in the appendix, we are quite happy with, but the overall idea is that brain deadly simple, but it works strangely well, which is kind of really nice to see. Meaning, the point is, you start with say with a product state or lower time state, and what you do is you evolve this many-body state under a plain vanilla TD-MAG, like a tensor network method, under this Hamiltonian from the given family of Hamiltonians, giving rise to an MPS. But we know how to exactly sample from MPS using this Ferris-Vidal method. I'm happy to say more about this. That gives rise to sampling. But then you can set up a log likelihood function and basically use a machinery of automatic differentiation and stochastic gradient descent, so methods from machine learning, to basically best fit the Hamiltonian given the data that you have. And then you do this and kind of learn the Hamiltonian given data and change the parts of the Hamiltonian to best fit the data that you see at the end. That's efficient in space and inefficient in time. It covers the Hamiltonians very well. That's kind of cute, because you get the Hamiltonian. Here's an example for Heisenberg type Hamiltonian that works generically very well, good accuracy, for very large system sizes, easily in the hundreds. And it's kind of cute because you can learn Hamiltonian to very good accuracy, but you cannot predict what comes out for late time. You can only learn the Hamiltonian, and then you have to go into the lab and make predictions. You use the learning just to learn the Hamiltonian, but you have to, time evolution being be complete, you have to go into the lab and do the quantum simulation where the learning is just used to build trust in the correctness of the Hamiltonian. It's quite cute. I spent a lot of time with experimentalists this week in Eisert who want to implement this, because they really want to know what they really have in the lab to high accuracy. In fact, we've done something very similar already for our friends at Google, who got, for better or worse, spectacular publicity with their quantum advantage experiment using the sycamore chip, where they found some paradigmatic problem that outperformed classical supercomputers for the same task. Not a practical one, but some task. I'm happy to show me more about this, but of course they're using a chip, and you want to know, is the chip doing what you think it's doing? Well, through an interesting coincidence, we ended up being the guys calibrating the chip for Google. In fact, this sycamore chip that was used for the quantum advantage experiment related to the fact is what they're doing, what they think they're doing. Yeah, and that's again the question at hand. And here we used ideas, I'm happy to say more about if you ask me, of super resolution and manifold optimization. So it's slightly different to basically calibrate their chip with hilarious outcomes. There's dark corners of dodgy bits and very nice chips and so on. But to be fair, it's like the best calibrated, also most accurate quantum simulator to date of this kind. If you see this as an analog simulator, so again, you can really very nicely learn what the Hamiltonian is and then make predictions for later times, having calibrated the device. Again, one can very precisely learn the Hamiltonian and then make predictions, and that's not always efficiently possible. So the learning things are just there to learn the Hamiltonian, and then you will make predictions based on the quantum data at hand, which is an intriguing state of affairs, I should say. 38 minutes into the talk, I think that's a good moment to stop. Outlook, so apologies, I made a bit of a tour through ideas that I found fascinating in the last year, hoping to stir up some interest along 3 lines of thought. In the first, more mathematically minded setting, although I went over it, but it should be clear that anything I said would be like rigorous in the sense of being theorems around this, and there's our rigorous statements. And making the point that random tensor networks are very nice tools, mathematical tools, theoretical laboratories, mathematical labs, to give rise to analytical insight that is even very much out of reach otherwise. We found that one can show equilibration to exponential accuracy for random matrix product states. We resolved the Brown-Susskind conjecture of a linear growth of complexity, which is nice. Again, without this machinery, it seems completely out of scope. here's hard work, but one can say something. It's a nice tool to have. David has done also beautiful work along these lines. It's kind of the idea of using random tensor networks to prove things otherwise out of reach. In the second shorter part, I said that we are working towards setting up libraries of numerical tools of tensor networks aimed at, well, supporting everyone, but in particular for us to support experiments with real quantum materials, because I find it fun to not apply only these methods to always the same Heisenberg models, but to actual models that actual people have in actual labs, giving rise to actual data and see what's going on. I think this is a nice premise to work with, and it's a wonderfully privileged position to talk to these people. And in the final part, I went really out of the box, saying that tensor networks are not only good in the quantum realm, which they surely are, but one can also think about probabilistic modeling or think of settings where tensor networks are set up to have bonds that label function dictionaries. And you can think of an entanglement theory in function spaces, which is a cute thing to have, but it's also practically minded because you can learn dynamical laws from data in a scalable fashion. And I think that's all I wanted to say today. And with this, I thank you very much for your attention. And I'm looking forward to questions you might possibly have.